Hello, everyone. Welcome to what will be the conceptual review for the final exam. And so this is going to cover a lot of material from the whole semester, and I'm going to go through it quickly, but obviously as I'm going through it, feel free to pause the video, write down notes as you need them. Okay. So we started the semester talking about phases of matter, in particular solids, liquids, and gases, and we can think of those in terms of their relative kinetic energies. And so gases have the most kinetic energy, solids have the least amount of kinetic energy, liquids tend to be in between. This relates to their intermolecular forces as well. So gases have the least amount of intermolecular forces, the most space between molecules, solid has the least, liquids are in the middle, right? And we talked about 5 different kinds of intermolecular forces. So a general term for intermolecular forces are van der Waals forces, just in case you don't remember that. The weakest of those are called dispersion forces, or occasionally London dispersion forces. Then we have dipole-dipole interactions, where we have molecules that have a dipole, they interact. Special kind, an extra strong kind of dipole-dipole interaction is a hydrogen bond, where a hydrogen is bound to either oxygen, fluorine, or nitrogen. And I did that a little out of order, but the Knopf monster is one way you could think about that or remember that. And with all 3 of those first intermolecular forces, they all have only partial charges, right? Then we have ion-dipole interactions and ion-ion forces, and the key difference with those is that they are interactions that are fully charged. So anytime we have an ion, we have a full positive and a full negative charge, depending on what we're actually looking at, right? Within that, if we think about what a dipole is, it relates back to electronegativity. So just a reminder that the general trend is that as we go up and to the right on the periodic table, our electronegativity increases, right? And these intermolecular forces affect a whole host of properties related to our molecules. So some of the main ones we talked about are viscosity, surface tension, adhesive, cohesive forces, and capillary action. Particularly if we think about like viscosity and surface tension, the greater the intermolecular force, the greater the viscosity, the greater the surface tension. Those are probably the most common ones, right? Another thing that intermolecular forces affect, since they affect the phase of our matter, is they will also come into picture when we talk about phase transitions. And so a reminder that when we have solid, liquids, and gases, if we go between a solid and a liquid, that is melting or freezing, depending on the direction. When we go between a gas and a liquid, we have vaporization and condensation. And then kind of the more exotic one, a reminder that when we go between solid and gas, that is sublimation. When we go between gas and solid, that is deposition, right? And so we can describe that qualitatively. We can also quantify the energy it takes to cause a phase transition. And so we do this in 2 ways. One of them is using this equation where we quantify our heat, which is Q, by multiplying by the mass times a specific heat times the change in temperature. And so a reminder, anytime we have a change in temperature, we do not have a change in phase. We have one or another. We're either going to be changing temperature or we're going to be changing phase. And if we change phase, we use this equation where we take Q times the number of moles, or Q being equal to the number of moles times a heat of either vaporization or fusion. And so that's could also be called an enthalpy of vaporization or an enthalpy of fusion. And so if we think about what a heating or cooling curve looks like, it should look like this, right? Anytime I have the blue here, we do not have a change in temperature, we have a change in phase. That's why our y-axis is temperature. And then anytime we have a change in temperature, we are in the red, where we have no phase change, so we're still in the same phase, but we instead change the temperature. Okay. Within that, we can also talk about the relationship between pressure and temperature and phase. And so a reminder that this is what a phase diagram looks like. And when you're going through this, your y-axis should be pressure, your x-axis will be temperature. Remember that a reminder that solid should be on the left side, gas should be on the right side, liquid should always be in the middle between them. Some other important points. We have a triple point at this branch where we have an equilibrium between all three of our phases. Anytime you cross one of these lines, you have a phase transition. And then once you hit a point called the critical point, you no longer have essentially pure liquid or pure gas, but kind of a new phase in between them called a supercritical fluid, right? Okay, so that covers basically our first chapter on to chapter 11, talking about solutions. So a reminder that a solution is a mixture, homogeneous mixture between a solvent and a solute. Solvent will be the majority component, solute will be the minority. And then we just, if we have a solid, dissolve it in a solvent like water, we would say it goes from being a solid to being dissolved. And so this is another sort of phase change, not really a chemical one, right? We can also form solutions between gases. So for example, if we have helium and argon, we open a valve between them, they will form a gaseous solution. And in order for a solution to form, we need our energetics to work. And so if we think back to the intermolecular forces, we have some sort of intermolecular force between our solute. We have some sort of intermolecular force between our solvent molecules. We need to put energy in to break those intermolecular forces. And if a solution will form, then the energy payoff, so we will have a greater energy release as we form new intermolecular bonds between our solute and our solvent. And that energy that we get from the release for the formation of those intermolecular bonds will be greater than the energy it takes to break apart our solvent and solute energies, break apart the bonds that hold them together through intermolecular forces, okay? Within that, we can think about how much things dissolve. So this gets back to talking about non-electrolytes, electrolytes, and weak electrolytes. And so it's essentially a measure of how much something dissociates. So something like ethanol will not dissociate when it's dissolved. And so we'd call that a non-electrolyte. Something like potassium chloride, we know will fully dissolve. That's a strong electrolyte. And then acetic acid, we know now that is a weak acid that only partially dissolves. And so we could call that a weak electrolyte, right? Next up, we can talk about solubility. So how much of something can we dissolve in a solution? A reminder that when something is saturated, that is the point at which something more of that solute will no longer dissolve, right? So even if we have, for example, a glass of sugar water and we reach the point of saturation to where we still might have sugar sitting at the bottom of our flask, we would call that solution saturated because that sugar sitting at the bottom of our flask will not dissolve. Anything that will still dissolve means that saturated or that solution is unsaturated. And then a reminder that supersaturation will require a change in either temperature or pressure. So you can think of kind of the classic example of a carbonated beverage is supersaturated, and then as it reaches equilibrium, it will become just saturated, okay? A reminder that solutions need to be miscible in order to form. So that goes back to the energetics of breaking the intermolecular bonds between our solute and our solvent to form then a new solution. We can measure concentration in different ways. So the kind of most used one that we use is molarity, that is moles of solute over liters of solution. However, volume is something that is temperature sensitive. And so we have some other measures of concentration. Reminder that if you're asked about mole fraction, that is just the number of moles over the total amount of moles in all of our components. We think about molality. Molality is kind of our weird one, where we have moles of solute over kilogram solvent. So molality is the only thing where our denominator, instead of being the whole solution, will just be the solvent. And a reminder that it's kilograms of solvent. And then we have different mass ratios. And so mass percent is just the mass of the solute over the mass of solution times 100. ppm, same thing, but times 10 to the 6th instead of times 10 to the 100. And parts per billion is, again, the same thing, but times 10 to the 9th instead of times 10 to the 6th. Okay. We have a whole class of properties called colligative properties, and these have an effect on phases. And so a reminder that a colligative property, something like freezing point depression, boiling point elevation, a colligative property in simple terms is something that is going to be affected by the quantity of solute in a solution, right? So it is something that is going to be affected by the number of particles that we have, okay? Great. Within that, a reminder of a few of our colligative properties. One of them is osmotic pressure. Pi is equal to our molarity times our T. That is just a measure of essentially how much pressure can be generated between a permeable membrane with different concentrations of solutions. We can also think about solubility in terms of gases and solids. The take-home point here is that typically speaking, solubility of gases in liquids goes down as temperature goes up. And again, typically speaking, solubility of solids goes up as temperature goes up. And so it's just a good trend to keep in mind. All right, that's chapter 12. On to chapter 13, kinetics. So we talked about this in class some, did some review problems, but a reminder that kinetics tell us how fast a reaction goes, not how far it will proceed. That's what we have equilibrium for. And we often describe this using rate laws. And so if we think of a general rate law, it is generally the rate of some sort of chemical reaction is equal to the change in the concentration of either our reactants or our products. If they are reactants, we have a negative sign over some amount of time. And so in this particular case, we would have negative change in concentration of hydrogen peroxide over change in time, right? We can express this in this form as well. This form takes into account the stoichiometry of a reaction. So a reminder that the stoichiometry is going to be 1 over whatever that coefficient is, multiplied by the change in concentration over the change in time, okay? And of course, that's what it could look like. How do chemical reactions happen is a good question. And so there are 3 components that we talked about that must happen. First is that molecules must physically collide. Second is that they need sufficient energy. So they need energy to break bonds. And then lastly, they need the correct spatial orientation. So they have to hit each other in the right way. And if any of those criteria are not met, then the reaction will not happen. Okay, so we can think of it in this example here. Whoops, going the wrong way. So within that, we also have something called a frequency factor that combines essentially 2 of those ideas, that molecules need to be oriented correctly, and also they have to hit a certain number of times. So the frequency of collisions is statistical based on pressure, volume, and temperature. The one we care about more is our orientation factor. So molecules that are spherical have an orientation factor around 1. Anything that is not a sphere will have an orientation factor of less than that, right? Okay, we also have activation energy to think about. So a reminder that our activation energy is starting at the reactants and then goes up to the top of our peak here. And so our activation energy could also look like that. It's always starting at whatever the reactants are and always going to the top of the peak, okay? And so that is what we call the activation energy. It is the barrier over which you need a certain amount of energy in order to overcome that and form your products. A reminder too that if we talk about our change in enthalpy, that is delta H, and that is our difference in energy between what we start with and end with. And so we have an exothermic and an endothermic example there. Okay. The most common way we express rates in kinetics is using rate laws and rate equations. So we went over this in class, so I won't spend a lot of time here, but generally speaking, our rate should be equal to some rate constant, lowercase k, times the concentration of one species to some power and the concentration of another species to another power, okay? And that has to be experimentally determined. It can't ever be determined by purely using theory. Within that, we can integrate those to get first order rate laws. And so this would be kind of the common form of our first order rate law. A reminder that with first order, what you're looking for are natural logs. So if we look at a graph and see a straight line and our y-axis is a natural log, we should think that is a first order rate, okay? For second order, it is 1 over our concentrations. So again, if you see a graph that has a straight line, it should be 1 over our concentration is equal to a second order rate law. And then finally, if our x-axis is just not modified with natural log or an inverse expression, if it's just the concentration and it produces a straight line, that will be a 0th order rate law. Okay. We also have half-life reactions. So if you're going to focus on one of these, I would recommend the first order half-life of a reaction that is equal to this 0.693, which is the natural log of 2 over k. The reason we care so much about the first order half-life decomposition is because it is not dependent on the initial concentration, whereas second order, 0 order do have a term for the initial concentration of whatever we're looking at, right? This is a summary. If you only want to study one slide from kinetics, this would be the one to do it, okay? So we also can talk about activation energy. Within this, essentially, reactions that occur at higher temperatures will have more molecules that are able to meet that activation energy. And so the reaction will occur more frequently. Okay? One way we can express that is using the Arrhenius equation. So it can take a couple of different forms where we have this form. We also have y equals mx plus b form. Essentially, what you're looking for is relating two rates with two temperatures, and that the slope of that line that you get will be equal to negative activation energy over R. And R, of course, is our gas constant there. So if you ever are given a table with multiple rates at multiple temperatures, think Arrhenius equation. Lastly, in kinetics, we have reaction mechanisms. And so these are the multiple elementary steps that make up an actual reaction. Reminder of some terminology here of an intermediate is something that is produced and consumed. So for example, we produce just O here. O is produced and then consumed. And so it is an intermediate in our reaction. If something is shown as a reactant first and a product second, we would call that a catalyst for the reaction. And so within that, our rate determining step will be the slowest step in our chemical reaction. The slowest step is of course called rate determining then, and that slow step will determine what our overall rate will be. So a reminder that the rate law cannot be written just from the pure stoichiometry of a reaction, but a rate law can be written from an elementary step. So if you know the elementary steps, you can write the rate law for a reaction, okay? So within that, that's basically the end of, one more thing to say on kinetics. If we have a catalyst, the catalyst will speed up the reaction, but it won't produce more product, right? So just a reminder, if we have a catalyst, it only affects the rate of the reaction, not how much is formed. All right, transitioning on to chapter 13, talking about equilibrium. And so equilibrium describes reversible reactions where we have this dual arrow here, and we can say our reaction goes both ways. Reminder that in chemistry, we talk about dynamic equilibrium, meaning that when we're at equilibrium, the forward reaction and the reverse reaction still occur, they just occur at the same rate. And so we don't see a net change in the concentration of our chemicals. Okay. All right, so within that, if we are not at equilibrium, we can determine where we are by finding Q. Q is calculated by taking the products over the reactants raised to their stoichiometric coefficients. And so this is how we would describe the concentration of something before it reaches equilibrium. Okay. Reminder too, I won't go through the slide, but you can modify K in a number of ways. Essentially, if you reverse the reaction, you take the inverse. You can also combine reactions to come up with an overall reaction. An important concept from equilibrium chemistry is Le Chatelier's principle. States that a system will respond to a stress by essentially adjusting the concentrations. And so, for example, if we were to add more reactant, if we had two reactants and one product, then more product would form in order to reestablish equilibrium, right? Within that, we can think about this in terms of pressure. So if we were to increase our pressure, we would essentially just plug in whatever our pressure change was into our Q expression. We would calculate Q, and so Q would be 3 times greater than K in that sort of case. And you can go through the math there on the slide if you have any questions. Temperature on equilibrium, the effect of temperature on equilibrium will also fall under Le Chatelier's principle. We can think of enthalpy as our heat, and so anything that is endothermic, we want to treat heat as a reactant, meaning that endothermic reactions will produce more products if the temperature goes up. And then the reverse is true. If we have an exothermic reaction, heat is considered a product, and so we would create more reactant if our temperature goes up. Right, and so here's, I guess, the catalyst slide that I thought should have been earlier. So a reminder that the catalyst does not affect how much of a reaction we get. It just changes how fast that reaction goes. Okay, this would be also a good slide to make sure you know every component on this. In particular, I will highlight transition states are at the top of our peaks. Intermediates intermediates will be in these valleys here between two peaks. And so those are ones that people oftentimes get confused about. And also just a reminder to be able to identify activation energy and enthalpy within these charts. Okay. All right. Shifting into chapter 14, talking about pH. So a reminder that how we calculate pH is by taking the negative log of our concentration of hydronium, H3O plus. We can go the opposite way by doing 10 to the negative pH to get our concentration of H3O plus. Same can be done with hydroxide. Very important thing to remember as well is that Kw is equal to our concentration of hydronium times our concentration of hydroxide, which at room temperature will be 1 times 10 to the negative 14th. Okay. All right, hopefully you remember all that. If we think about the pH scale, things that are less than 7 will be acidic, greater than 7 will be basic. Then we can also talk about our different definitions of acids and bases. So a reminder that arrhenius acids produce H+, arrhenius bases produce OH-. We have Bronsted-Lowry acids and bases. The Bronsted-Lowry acid produces H+, Bronsted-Lowry base accepts H+, so everything is defined in terms of H+. Finally, we have Lewis acids and bases. A Lewis acid will accept in a lone pair of electrons, a Lewis base will donate an electron pair. And so for Lewis acids and bases, everything is defined in terms of electron pairs. Reminder again, make sure you memorize what's a strong acid, what's a strong base. Everything that is not those will only partially ionize to be a weak acid or a weak base, right? Within solution then, we can calculate the Ka or the Kb of a system by taking our products over our reactants for the dissociation of an acid or the production of the ionization, I guess I should say, of a base, right? So you could think about this slide, what's our strongest acid, what's our weakest base? A reminder that the thing with the largest exponent, so in this case 1.2 times 10 to the negative 2 is what we would want to look at. That's going to be our strongest acid. The strongest base for a given Kb will be, again, the largest exponent, and so that would be our strongest base. The opposite then is true, so if we think of this top one, our weakest acid / strongest conjugate base would be this 1.8 times 10 to the negative 5th, okay? Right, so a tricky part of acids bases is when we start with a salt instead of the pure acid or the pure base. So for example, say we start with the salt ammonium chloride. and that dissociates to form ammonium and chloride. Ammonium will react with water to make it acidic. Chloride is the conjugate base of a strong acid, right? HCl. So that reaction won't actually happen there. And we would just have chloride as a spectator ion instead of affecting the pH. Same would be true for something basic, where if we start with a sodium acetate, our acetate can react with water, make our solution basic. Sodium is the conjugate acid of a strong base, and so it won't have an effect on our pH. Okay. Next thing, we have buffers. So a reminder that a buffer is something that resists changes in pH, and that is done by having both a weak acid and its conjugate base present. Reminder that you can't make a buffer with a strong acid or a strong base. It must be a weak acid and a weak base. Okay, so as we add, for example, more hydroxide, that would react with the acidic portion of our buffer to form more of the basic portion of our buffer, and then vice versa for the acid if we were to add acid. Okay. Anytime you read the word buffer, hopefully this is ingrained in your mind at this point, is you need to use the Henderson-Hasselbalch equation. And so its derivation is shown here if you care. If you don't, Henderson-Hasselbalch is pH is equal to our pKa plus the log of our base over our acid, right? So that's very important. Again, anytime you read the word buffer, if you have a buffer, think Henderson-Hasselbalch. Also a reminder with buffer problems, instead of doing just an ice chart, anytime we have a buffer, do a BCA chart. And so for buffer problems, as well as titration problems, we will be adding a strong acid or a strong base. If we add a strong acid or a strong base, the reaction goes entirely to completion, meaning we use a BCA chart. And then if we're doing something like a titration, we can do an ice chart. If we have a buffer, we can use Henderson-Hasselbalch, right? That leads us to titrations, in fact. So a reminder that if we have something like a strong acid and a strong base being titrated, our equivalence point will be 7. If we start with a weak acid, our equivalence point will be just weak conjugate base being present, meaning that our overall pH will be basic instead of neutral. And everything before that should fall in a buffer region, right? And so once we start adding our titrant, we can calculate the pH using Henderson-Hasselbalch. Otherwise, we need to, at the equivalence point, calculate the pH by figuring out how much of our conjugate base we have produced and doing an ice chart at that point, right? Same could be true if we start with a weak base. Our pH starts high because we're starting with base. We have a buffer region still and a half equivalence point. Another thing that I did not mention on this previous slide that is on this slide is that our half equivalence point is very important because our half, again, reminder, half equivalence point where our pH is equal to pKa. And so that would be, for this example, ammonia's pKa is 9.24 because its pH at the half equivalence point is 9.24. It is when our concentration of weak base and conjugate acid are equal to each other, right? We can also have a polyprotic acid curve. This is what it looks like. I won't say much more than that. Okay. Right, our second to last kind of equilibrium, solubility equilibrium. So KSP is when, if you see KSP, what I want you to think is start on the reactant side with some sort of solid, and your products will be that solid dissociating into things that are aqueous. Your KSP expression should then be just your products. You shouldn't have reactants as part of your KSP expression because your reactant will always be a solid. We don't include pure solids or liquids in our equilibrium expressions, right? So the general formation of that, again, it's products over reactants, should look like that. The KSP value can then be determined if you're given equilibrium concentrations in molarity, or you can figure out the concentration in molarity for some salt if you're given the KSP value, right? Another thing that can affect solubility, so KSP, is if we have a common ion. So for example, if we have silver iodide here, then if we had another solution of like some sort of silver nitrate, something that is soluble, or sodium iodide that is soluble, having that common ion present would affect the concentration of our silver iodide. You can also think of this example with magnesium hydroxide. Okay. Lewis acids and bases, just another look at those. So a reminder, we have donation of an electron pair there from our Lewis base to our Lewis acid. We have another example there. Okay. Right, finally, final form of equilibrium is Kf. So a reminder that Kf is our formation constant. This can also oftentimes be coupled with our KSP equilibrium, where say we start with some sort of ion, it reacts with some sort of, so we could also define this as some sort of Lewis acid and a Lewis base, and we define this as products over reactants, raised to their powers, of course. One thing in particular about Kf will really always have large values. So if you see something like times 10 to the 7th, that is generally indicative of a Kf value. This can also increase solubility of things. So in this example, we have silver chloride that has a KSP value of 1.6 times 10 to the negative 10th. However, if we add ammonia in, we get a Kf equilibrium, and that would help make the overall solubility increase. And so our new K value would be 2.72 times 10 to the negative third. Just a reminder there. Okay. All right, on to chapter 16, I think. Penultimate chapter, talking about thermodynamics. A spontaneous process is something that will occur naturally under certain conditions. Non-spontaneous will not occur unless there is external energy input. Okay. We often define this in terms of microstates. So a reminder that a microstate is a way in which we can arrange energy or matter within a system. The more microstates we have, the greater potential for energy that we have. Okay, that's defined in terms of Boltzmann equation. So S, which is again entropy, is equal to our Boltzmann constant times the natural log of W. Essentially, as our number of microstates increases, the entropy of our system increases. That also helps us define the third law of thermodynamics. Reminder that the third law of thermodynamics states that the entropy of a perfect crystal at 0 degrees Kelvin has an entropy of 0. This is a theoretical construct, but it does give us an absolute value for entropy. Also a reminder that molecules that, if we take it all the way back to our first unit, we will have increasing entropy as we increase the kinetic energy of our phases. So solids will have less entropy than liquids, which will have less entropy than gases, right? We can calculate entropies in a couple of ways. One would be taking the sum of tabulated values of entropies, do products minus reactants, multiply it, of course, by their stoichiometric coefficients. We can also think of the second law of thermodynamics, where a reminder that the second law states that all spontaneous changes cause an increase in the entropy of the universe. Even if the entropy in our system decreases, we can still increase the entropy of our surroundings to make a process spontaneous. And when we're talking about spontaneity, what we're really talking about is Gibbs free energy. And so this is the main way that we typically quantify Gibbs free energy. This relates enthalpy and entropy and temperature. And what Gibbs free energy is the maximum amount of usable energy or work that a reaction can produce, right? Also a reminder that delta G values that are negative will be spontaneous or favorable, we could say. If we have a positive delta G value, that is something that is unfavorable or non-spontaneous at that temperature and under those conditions, right? Reminder, this would be another good chart to think about if you don't already have this memorized, that some processes will always be favorable, some processes will always be unfavorable, and then some are in the middle that are dependent on temperature. Okay. Gibbs free energy can be calculated in these ways, similar to our entropy. We can also relate Gibbs free energy to our equilibrium constant, K. So a reminder that if we have a negative delta G value, K should be greater than 1, vice versa. And then if we're under non-standard conditions, we would use this equation where K becomes Q, and we move our standard Gibbs free energy over to this side of our equation. Okay. Final unit, electrochemistry. So a reminder that a reduction oxidation reaction will occur. If we have one reaction, for example, if we have oxidation, we must have reduction as well. There's an example there. And then if we construct an electrochemical cell, we will get spontaneous flow of electrons if it is a voltaic or galvanic cell. That will also mean that our redox reactions happen at a cathode. So a reminder that reduction always takes place at the cathode, oxidation always takes place at the anode. And then if we get a positive cell potential, that means that we have a galvanic cell. And vice versa, for a non-spontaneous cell, we'll have a negative cell potential. Okay, and that is all relative to our standard hydrogen electrode that has a value of 0 volts. Okay. Within that, things that we often have tables called reduction potential tables. Things that are more positive are more oxidizing. Things that are more reducing are more reducing. We tend to relate our Gibbs free energy to our cell potential using this equation. We can also relate it to our equilibrium constant, and of course, make our magic triangle. We'll state again, when K is greater than 1, the reaction is favorable. When K is less than 1, it is unfavorable. Delta G will be negative for favorable processes, positive for unfavorable processes, and our cell potential will be positive for favorable, negative for unfavorable. Okay. Final thing is that our Nernst equation also exists. So our Nernst equation will be used anytime we're under non-standard conditions. This is what it looks like. It will be included on your equation sheet. Oh, and I guess final thing, we can also think about electrolytic cells that are non-spontaneous processes that can be essentially running our galvanic cells in reverse electrochemically. Okay. That's all I have. That's all Gen Chem 2. Good luck studying. If you have any questions, please let me know. Otherwise, I will see you in class.